Way 29 deals with radioactive decay. When you have an unstable atom, it's going to emit energy in the form of some type of particle, radioactive particle, to become a more stable isotope. When we want to look up the type of decay an unstable nuclide undergoes, we use table N. So, for example, carbon 14, it decays via beta minus decay, and its half life, the amount of time it takes for half of these isotopes to transform into a more stable isotope, is indicated by this column here. So a lot of these problems will feature use of table N in identifying decay modes or how long the half-life takes. Let's try some problems. The diagram below shows the first three steps in uranium-238 radioactive decay series. So here it shows uranium-238 undergoing alpha decay into thorium-234. It's not known what type of particle gets released to transform from thorium-234 into palladium-234, and it tells you that palladium-234 decays into uranium-234 via beta minus decay. The decay mode for the first and third steps is shown above the arrows. The decay mode for the second step is not shown. It's indicated by this question mark. Thorium-234 has a half-life of 24.10 days. Identify the decay mode particle emitted from the thorium-234. So for these problems, you have to remember that the mass going in needs to equal the mass going out, and the same goes for the atomic numbers. So when doing problems like these, it helps to draw a nuclear equation. So when we do that, we need to find the missing particle such that thorium-234 produces palladium-234 plus some particle. So think about what mass is missing here and what atomic number is missing here such that when I add this mass to 234, I get 234. And when I add some number to the atomic number, 91, I get 90. So for this equation to be balanced, we know that the missing particle's mass has to be 0 and the atomic number has to be -1. Why? Because 234 plus 0 equals 234, and 91 plus -1 will give you 90. So this type of particle is beta decay. So all you have to simply write is beta decay. Notice that on table N, it's not indicated what thorium-234 undergoes. Therefore, you have to physically calculate using the nuclear equation. Let's try another problem. An unstable nucleus spontaneously releases a positron. This is an example of if you recall, unstable nuclei releasing positrons is just a form of radioactive emission. And this is always an example of radioactive decay. So the answer is 1. Which radioisotope has the fastest rate of decay? In order to do this problem, you need to look at table N and look at all the various half-lives for each of these isotopes. The one that undergoes the fastest rate of decay would be shorter or longer. Think about that as you answer this question. Okay, if you look up carbon-14, it takes 5,715 years to decay versus calcium-237, which only takes 182 milliseconds. Look up iron-53, it takes 8.51 minutes, and potassium-42, which takes 12.36 hours. Thus, the one that's the fastest is the one with the shortest half-life. Therefore, the answer is calcium-37. Next problem. Which phrase describes the decay modes and the half-lives of potassium-37 and potassium-42? Once again, in order to identify the decay mode and the half-life, we have to use table N. So look at this table and decide what the correct answer is. Notice that potassium-37 takes 1.23 seconds to decay, and potassium-42 has a half-life of 12.36 hours. Therefore, they have different half-lives. And notice the decay mode for potassium-37 is beta plus, and potassium-42 has beta minus. So they also have different decay modes. Therefore, the answer choice is 3. Compared to the half-life and decay mode of the nuclide SR90 and the nuclide Ra226 has, so once again we have to use table N to compare the nuclides SR90 and Ra226. Okay, notice that Ra226 has a half-life of 1599 years and undergoes alpha decay, whereas SR90 has 29.1 years as a half-life and undergoes beta minus. Therefore, compared to SR90, Ra226 has a longer half-life and a different decay mode. The answer choice is 2. Next problem. Says some isotopes of potassium-37, potassium-39, potassium-40, potassium-41, and potassium-42 are shown in the table below. The natural abundance and the atomic masses for the naturally occurring isotopes of potassium are shown in the table below. Identify the decay mode of K37. Remember, anytime you need to identify the decay mode of a particular isotope, we use table N. Go ahead and do that now and see if you can figure out the answer. Okay, this is as simple as looking at potassium-37, and we see that its decay mode is beta positive decay. Illuminated exit signs are used in public buildings such as schools. If the word exit is green, the sign may contain the radioactive isotope tritium, hydrogen-3. The tritium is a gas sealed in glass tubes. The emissions from the decay of tritium gas causes a coating on the inside of the tubes to glow. Complete the nuclear equation below for the radioactive decay of tritium by writing a notation for the missing product. Once again, we're looking for the nuclide symbol such that the masses in equals the masses out, and the atomic numbers in equals the sum of the atomic numbers out. So see if you can figure out what the missing value is, both the mass and the atomic number. Okay, you should have gotten helium-3 with an atomic number of 2. Why? Because 3 plus 0 gives you 3, and 2 plus negative 1 equals 1. Which radioisotope is matched with its decay mode? Once again, you need to utilize table N and match each nuclide with the corresponding decay mode and figure out which one of these is correct. The only nuclide correctly matched with its decay mode is potassium-32 and beta minus. Therefore, the answer is 4. Okay, hopefully this was helpful. Thank you for watching.